at the time I record this video. The information it contains cannot be known to anyone on Earth but me. At least, such a situation seems to be the most likely. But if you watch this video to the end, all the secrets of gravity that I know will become available to you too, my dear viewers. And I clearly anticipate your purely reflexive reaction to them. A reaction of deep psychological rejection. Nevertheless, I beg you not to rush to final conclusions. At one time, the theory of relativity and quantum mechanics caused exactly the same reaction, but they still exist successfully. Because despite all their seeming insanity, they are based on rigorous mathematics and are perfectly validated by physical experiments. The secrets of gravitation outlined here are also based on rigorous mathematics, and they are actually validated by all those experiments that support the general theory of relativity, although it would seem to be a completely impossible thing. How can the same physical experiments simultaneously confirm the statements that are opposite in their physical sense? An extremely confusing situation at first glance. And in order to make it as clear as possible, I will have to preface the revelation of my secrets with some explanations. I will try to make them as short as possible, so as not to bore you, my dear viewers, and as clear as possible, so as not to confuse you completely. Thank you in advance for your patience. So, one of the modern theoretical physics foundations is the Standard Model, which describes the structure and behavior of matter at the microscopic level. Its predictions are confirmed experimentally down to millionths of a percent. Therefore, it is considered to be very accurate and correct. However, it does not describe all the fundamental interactions of nature. Gravitational interaction is described by another theory, the general theory of relativity, created by Einstein in 1915. The predictions of this theory have also been repeatedly tested experimentally and confirmed with the highest degree of accuracy. Therefore, it is also considered correct and very accurate. It would seem, after the creation of such remarkable theories, truly golden times were to come for physical science, and our understanding of known physical phenomena should now be considered complete, at least in its most fundamental basis. However, the clear skies of theoretical physics are still obscured by a minimum of 3 dark clouds that do not want to dissipate. Their names are dark matter, dark energy, and quantum gravity. It is about the last of them I am going to start my discussion. Back in the early 20th century, it was firmly established that all those particles of which the matter of the universe is composed, including you and me, are not actually particles in the usual sense of the word. After all, how do we usually imagine particles? As some material points, having certain masses and sometimes charges. Their location at any moment of time can be described by just 3 numbers, representing spatial coordinates in one or another frame of reference. However, this description turns out to be just an approximation to reality. This approximation works all the better the larger the mass of the particle. But when the mass of the particle is so small that it is comparable, for example, to the mass of an electron, this approximation does not work at all, because such particles actually behave as quantum objects, namely as particles and waves at the same time. And quantum objects require quite a different description: quantum mechanical. Physicists successfully coped with the problem of creating a quantum mechanical description of particles at the first quarter of the 20th century. A truly triumphant crowning achievement of their work was the Dirac equation, which not only correctly explained some subtle effects of atomic spectra, but even predicted the existence of antiparticles. However, physicists almost immediately faced the need to solve another quantum problem. The fact is that particles are sources of various fields. Of these, the most noticeable in the literal sense is the electromagnetic field. After all, the light we see is nothing but a stream of electromagnetic waves of very high frequency. Until the beginning of the 20th century, physicists did not know at all about the existence of fields other than electromagnetic and gravitational ones. Naturally, physicists very much wanted to get at their disposal a theory that would correctly describe the relationship between the electromagnetic field and its sources in the form of charged quantum particles. Maxwell's theory of the electromagnetic field, which already existed at that time, was not suitable for this in any way, because the sources of the Maxwellian field can only be classical, not quantum-charged particles. That is, such particles which at any moment of time have exactly defined spatial coordinates, what is not observed in nature, as we have already noticed. Maxwell's theory and the theory of quantum particles are just mathematically incompatible with each other. Similarly as one addition operation cannot be performed over two vectors of different sizes. Full mathematical absurdity turns out. In short, the problem is quite obvious, and theoretical physicists began to solve it. Their efforts were successful and led to the creation of quantum electrodynamics, the first quantum field theory. Along the way, they created quantum theories for two other fundamental interactions, the weak and the strong, which were discovered in experiments with charged particle accelerators. All these three theories, that is quantum electrodynamics, electroweak theory, quantum chromodynamics, as well as the Higgs field theory, now constitute the above-mentioned standard model. But where is the place for the quantum gravity in it? If you, my dear viewers, are also interested in this question, you are absolutely right. Because the source of the field, which is described by general theory of relativity, can be only classical, not quantum particles. And it means this field must be quantized in some way. Unfortunately, it is mathematically impossible to do it in the ways used to construct the standard model. The main reason for this is that the standard model considers its fields as different kinds of matter. Moreover, the presence or absence of such material entities in space in no way affects the properties of space itself, and also the properties of time. On the other hand, the general theory of relativity treats the gravitational field as something absolutely immaterial, namely, as a curvature of space-time geometrical properties. Hence the main reason for the incompatibility of the standard model and the general theory of relativity. Those techniques, which are applicable for quantization of matter, are absolutely inapplicable for quantization of space-time geometry. Attempts to combine one with another lead to mathematical and logical absurdities. With the same success it is possible, for example, to define taste of rainbow or color of number 42. It also turns out to be a complete nonsense. Of course, physicists try to resolve this contradiction. They built various theories, like superstrings or loop quantum gravity. However, these theories have one common flaw. All of them are based rather on frankly unbridled fantasy of their authors than on firmly established facts. So that by now, theoretical physics has been in a very strange situation, resembling an apparent semantic dead end, from which there seems to be no obvious way out. In view of all these sad circumstances, I have two pieces of news. One is very good, and the other is very bad. I will start with the very good. Otherwise you, my dear viewers, may not understand the essence of the very bad. First, as I have found out, the equations of general relativity are extremely precise. It is highly unlikely that more precise equations can be derived in the realm of non-quantum and perhaps non-cosmological physics. This is truly the limit of non-quantum perfection. Secondly, the equations of general relativity themselves do not contradict the fundamental principles of the Standard Model in no way, for which I have a corresponding mathematical proof. The seeming contradiction is just a historically formed misunderstanding, which is quite possible to overcome. In this regard, let me further elaborate on how exactly I managed to do this. There is one mystery connected with Einstein's personality, which at one time I wanted to solve perhaps no less than all the other secrets presented on this channel. Being one of the founding fathers of almost all modern branches of physics, since the 30s of the last century, he suddenly went into a deep scientific reclusion. Most physicists consider his works of this last Princeton period, to put it mildly, unpromising, because of the absolute ignoring in them of the quantum physics achievements. First of all, the strong and weak nuclear interactions, which were discovered during his lifetime. What made him sharply reduce his scientific productivity? The first possible reason that immediately comes to mind is the negative effect of age on intellectual ability. But this explanation does not stand up to any criticism. Einstein remained a brilliant thinker until the end of his life, and mastered mathematics not any worse than in his earlier years. Naturally, I was not the only one who paid attention to this mysterious metamorphosis of Einstein. Many studies have been devoted to this topic, which continues to be interesting and relevant up to now. For example, relatively recently, the well-known science writer David Bodanis published an entire book entitled Einstein's Greatest Mistake. Its content is quite profound, and its style is no less brilliant in form for me to risk spoiling the impression of it with my wretched English. Therefore, I will not retell this wonderful book, but I will strongly recommend you to read it in the author's own words. Believe me, it's worth it. As for me, my interest in the mystery of Einstein's last years was driven by a purely pragmatic consideration. Its essence lies in the distinct realization of the fact that the old seasoned hunter for scientific treasures Einstein suddenly began to dig in only one place. And he was doing it for more than 20 years, almost completely abandoning all his other scientific endeavors. In addition, he did not pay any attention to the frankly negative impression that he made on his colleagues with such a strange, from their point of view, passion. And yet he remained sane and of sound mind. What could possibly account for such a seemingly paradoxical combination of circumstances? Damn it, there can be only one reasonable explanation. In the place where the old seasoned hunter for scientific treasures digs long and hard, really should be buried scientific treasure, and its value is sure to redeem all the effort required to retrieve it. A very simple consideration, even primitive. Philosophers and psychologists would probably disagree with such a straightforward approach. However, my life experience suggests that the simpler the explanation, the less likely it is to be wrong. Occam's razor, so to speak. Therefore you, my dear viewers, should not be surprised at all that I started to study theoretical physics seriously when I was already far over 30. And I am a computer specialist and an applied mathematician by education, not a physicist at all. I just felt a chance that comes once in a lifetime, and not for everyone. However, not only this circumstance motivated me to study theoretical physics. Shortly before that, I invented the calculus of virtual numbers, which I talked about in my previous video. You can find a link to it in the description. I wanted to check whether this calculus could be useful in any other fields of science besides applied mathematics. As it turned out, yes. At least for physics it is indeed so. For example, there is such a course of theoretical physics by Landau-Lifshitz. It is considered very sophisticated and advanced. Some Nobel laureates took their formulas exactly from there, and the mathematics used there is so complicated that not every profile specialist is able to understand it clearly. However, to my great surprise, I did not have any such problems. And not at all because I have any outstanding scientific abilities. Throughout my entire conscious life, such abilities remained with me at a rather mediocre level, I have to frankly admit it. If I have had research success in anything, it has been at the expense of a very different ability that is truly unique. It is the ability to see through the obviousness filters and to consciously control this vision. I also talked about the psychological phenomenon of obviousness filters in one of my previous videos. You can find a link to it in the description as well. So, the secret of clear understanding the Landau-Lifshitz course turned out to be very simple. If some part of mathematical calculations which are given there are translated into the language of calculus of virtual numbers, and if apply one wonderful mathematical invention of Sir Roger Penrose, pseudo-inverse, they become clearer many times. However, their volume also increases a lot. But this is not a price for clear understanding to be paid with regret. Personally, I managed to notice very subtle and non-obvious mathematical nuances, thanks to which I even found some serious errors in this course. For example, this one. Agree that such test results of a new theoretical tool should be considered more than successful. The mystery of the last decades of Einstein's life was also dealt with quite successfully. Einstein quite correctly supposed that electromagnetic and gravitational fields should be described by a single relativistic theory, even if not quantum one. This is clearly indicated by the fact that these fields have many common mathematical properties. For example, in the region of weak values, their strength satisfies the inverse square law. From their sources, they propagate at the speed of light. These sources themselves satisfy the corresponding conservation laws. The Lagrange functions in the classical approximation have absolutely identical algebraic structure, and so on and so forth. Is all this multitude of common properties the result of mere coincidence? Of course not. Such an option is extremely unlikely. It is much probable that common properties of electromagnetic and gravitational fields are consequences of some unified relativistic regularities. Therefore, it would be very reasonable from our side to try at first to deduce these unified relativistic regularities from already known common properties of fields by inductive method. Then, in case of successful completion of the first research stage, to verify the obtained result by the opposite method, deductive. That is, to thoroughly check the consequences of the obtained unified regularities for their correspondence to reality. And also on the subject of what new scientific information such consequences can give. a highly reasonable and promising scientific program, which Einstein actually pursued during the Princeton period of his life. But why did he receive such negative evaluations from his fellow physicists? Well, simply because his colleagues clearly saw how Einstein used very doubtful theoretical tools to realize his scientific plan. And this vision prevented them from seeing the very essence of Einstein's program, from seeing its extreme clarity, crystalline purity, and quite ordinary for Einstein genius. What can you do? Physicists are human beings too, and therefore they are all subject to the negative influence of obviousness filters. Einstein simply did not have the necessary theoretical tools at his disposal, and he endured this drama with a truly stoic humility. It so happened that the tools so necessary for Einstein were collected by me only 60 years after his death, and this circumstance gives me the full moral right to proclaim that Einstein's Princeton reclusion was not at all an oddity of a genius who had gone out of circulation. In fact, it was very useful work. He may not have gotten the final result, but the unbending persistence with which he pursued it clearly demonstrated the right path that we, the inheritors of all his scientific treasures, should have followed. This way has been finally passed, and now I have an honor and an opportunity to present to your attention, my dear viewers, the equations which describe the unified relativistic regularities of electromagnetic and gravitational fields. Without Einstein's inspiring example, they would never have seen the light of day. To write down these equations, I had to use such mathematical tools which have not been used anywhere else before. Therefore, they may require deciphering even for those of you, my dear viewers, who know the mathematical apparatus of modern theoretical physics perfectly. But if you are not curious about pure mathematics, just go to the next part. There you will find a really interesting surprise and a completely unexpected twist in my story. So, returning to our equations. First of all, I would like to note the following groups of symbols. These are infinials. They are a kind of natural generalization of the concept of differential, and lie at the heart of my calculus of virtual numbers. As I said earlier, you can learn about it from my previous video. The next obscure symbols contain many dots. These are tensor patterns, another of my mathematical innovations. They symbolize the basic characteristics of fields and their sources. Z is the charge pattern, J is the charge current pattern, and psi is the field potential pattern. Nature is arranged in such a way that the above characteristics are expressed by tensors. But for electromagnetic and gravitational fields, the corresponding tensors have different ranks, and therefore must contain different sets of tensor indices. The dots symbolize the places where the corresponding tensor indices, needed in a particular case, should be substituted. If the rank of a tensor exceeds 1, it must be symmetric in all its indices. Finally, the symbol M is labeled with an asterisk, which is completely uncharacteristic of Maxwell's and Einstein's formulas. The asterisk means that the so-called rest or invariant mass M is not really a constant, but can change under the influence of the field. In the purely electromagnetic case, this doesn't happen. But if we don't take into account this mass shift in the case of gravitational interaction, we come to a mathematical contradiction. The system of the first three equations turns out to be unsolvable. This effect is actually very important. It is due to it that the geometry observed in the gravitational field is non-Euclidean. One of the reasons of failure in the construction of the quantum gravity on the basis of the linearized general theory of relativity was connected with the non-accounting of this effect. The physical sense of the presented equations is quite simple. The first equation means that the total energy momentum of matter in a field is the sum of the kinetic and potential components. The second equation states that the total action of matter in a field consists of the action of matter itself and the action of its interaction with the field. The third equation connects the kinetic energy momentum of matter with its four-velocity bi-relation, well known to physicists. The fourth equation expresses the conservation law of field sources. For the electromagnetic field, it is the conservation law of electric charge. For the gravitational field, it is the conservation law of energy momentum. The fifth and sixth equations are essentially a single construct. It means that there are special gauges for the potentials of massless fields. And these gauges transform the relations between the potentials of such fields and their sources into wave equations of D'Alemberian type. Or to put it quite simply, weak electromagnetic and gravitational fields propagate from their sources at the speed of light, and their strength satisfy the law of inverse squares. If we take the scalar E divided by C as the charge pattern and the vector A as the potential pattern, we get Maxwell's equations and the Lorentz force. If we take the energy momentum vector P as the charge pattern and the tensor psi as the potential pattern, we get Einstein's equations. The tensor of gravitational field potentials are denoted by the letter psi instead of G, because the letter G is used to denote the metric tensor of the geometry observed in the gravitational field. These tensors are not, generally speaking, identical, but they are so similar in their mathematical properties that when calculating variational derivatives, like this for example, you can safely change the variation of psi to the variation of G. The correctness of the final result will not be affected. By the way, it was due to this circumstance that Hilbert obtained the correct equations of the gravitational field in 1915, although he varied the components of the metric tensor G rather than the true gravitational potentials, which make up the tensor psi. I would also like to notice that in the general relativity, it is somehow not accepted to use such a concept as inertial reference frames. Whereas in all other, that is non-gravitational physics, this concept has a fundamental character. It turns out a very strange situation at first glance. What in one part of physics has a fundamental character, in another part seems to be of no importance. In fact, fundamental concepts cannot just disappear. And in the general relativity, the inertial reference frames are actually present too. But there, they are simply designated by another name. Gravitational physicists prefer to call them harmonic coordinates. Only one of the scientists known to me dared to call them by their real name, and only in private correspondence. This is Vladimir Alexandrovich Fock, a world-famous Soviet theoretical physicist, now long deceased. The unified regularities of the electromagnetic and gravitational fields, demonstrated now on the screen, also explain why under the influence of the gravitational field, the observed geometry of space-time becomes non-Euclidean. And this non-Euclideanism appears not in the most general Finsler form, but exactly in the pseudo-Riemannian, that is, bilinear form. And why Einstein's equations, in fact, do not contradict the fundamental principles of the Standard Model at all. In short, thanks to these equations, now we have a full theoretical harmony and complete absence of logical and semantic obstacles to begin the procedure of quantization of the gravitational field. Well, now let me pass to very bad news.